Hello. So in this presentation, we're going to talk primarily about a lot of different ways we can address memory to move a certain number of bytes from memory into a register. But before we do that, I'm going to review a little bit of what you did in the last activity. So in the last activity, you had code that looked like this, and I had described in the last presentation how this pointer dereferencing matched directly the idea of taking data that XP was pointing to and going into memory and getting it. So here RDI contained XP, and then after this instruction is executed, RAX holds the value that was in memory. So it's akin to having T0 in the RAX register. And this type of memory addressing is how we do this pointer dereferencing. Now, in this case, the dereferencing is on the right-hand side of this assignment and ends up on the left-hand side of this move. So remember that, and hopefully you might have noticed that when you were looking at this code. But if not, note that, because it can be on the left-hand side of the assignment and then goes on the right-hand side of the move, which we will now see in this code as we go through it. So you looked at this in activity 2. I'm going to review that code now just to make sure you followed what was going on there. So here's that swap function that was in that activity 2. And below it here is the assembly code for it. And now here are some comments where I put in simply what the corresponding C code lines are. If I were to do this even more carefully, I probably would have put another statement here that said, now RAX has T0, for example. So that's what I would suggest you get used to doing, because it's helpful to remember what each of the registers has in it as you're going along looking at this code. Okay, so now when we were doing this, of course, we needed to remember that the convention is that when this function swap gets called, the parameter XP is in RDI and the parameter YP is in RSI. And so that's shown in this picture here, where RDI has a pointer, an address in memory where a particular value is located, as does RSI. And so now let's look at a concrete example of this sort of thing. We start with this notion here. RDI has XP, RSI has YP. So now if we look at an actual example, suppose that RDI has this value, and that corresponds to an address in memory that's holding the decimal value 123 in these 4 bytes. Let's say it's an integer. And then next, well, let's say it's a long, and this is every 2 bytes. That's what I'm showing here, is every 2 bytes, and just to make it a bit more compact. And then RSI, remember now, contains YP, right? And so RSI is this address, where again, a long whose value is 456 is stored in memory there. And so this first line of the swap code is basically taking that 123 that XP is pointing to and putting it into the register RAX. And then this next line of code is similarly taking what RSI is pointing to, and RSI is 0x100, and here's the 0x100 over here, and it's taking and putting 456 into RAX. And then the next line of code, now here's where, remember a minute ago I said, oh, you know, this pointer dereferencing can occur on either side of an assignment statement. Well, now it's over here on the left-hand side. And so what are we doing? We're changing up the move so that now we're taking a value and putting it back into memory where RDI is pointing. So we're taking the value that's in RDX, which is our 456, and we're moving it to where RDI is pointing to. So 456 is now up here. And likewise, the next statement is basically taking what's in RAX and putting it down into where RSI is pointing. And so this is a very simple yet classic example of how the pointer dereferencing works at the assembly level and how we can move data from one place to another by using the registers in this way. And these temporary values in C correspond to using temporary registers in the assembly language. So that's how that example works. Now what we're going to do is we're going to look at some more complicated memory addressing modes. And so we first off have simply had the one set of parentheses and used it for pointer dereferencing. This is a normal memory addressing situation. Well, we can create some much more complicated ways of getting to parts of memory with some different addressing modes. The first simplest one is to add a displacement to the front. So you'll see here, now we've put an 8 there. So we're going to go into memory where RBP is pointing to, but then we're going to add 8 bytes to it. And so we're going to go down in memory 8 more bytes and then get the value pointed to there. And in a little while, I'm going to show you why we have these different kinds of modes. So this is the next simplest mode, is to simply have a displacement. The most general form of this looks like this, where we can have the displacement. We can have the RB, what's called the base register, and then we can have another register name, and we can have something called a scale. And all of this is used to come up with a different place in memory to go to by saying, take what's in register RB, add this scale times what's in register RA, and then add in this displacement. So this is the most general form of this, and I'll give you an example of how we often use this in code in just a moment. So why this scale of 1, 2, 4, or 8? That's because these are the sizes of data types and pointers, and it's the same reason that D is also divisible by 1, 2, 4, or 8, is because we're going to go into memory either in 1 byte chunks, 2 byte chunks, 4 byte chunks, or 8 byte chunks. Okay, so there are some interesting special cases. So we might not always have all 4 of these, D, RB, RI, and RS. And here's some examples of some of these special cases. And so the idea here is that we might not have an S. And so if we don't have an S, that implies that it is 1. And so we could have an RI but not an S. We also could have no D here, and that would imply that that's 0. We'll just add 0 or not add anything at all if there's no D. We could have no RB, and that means that one should be ignored. And so we'll see that we'll see that's this one right here where there's no RB, right? And we can have no D. And you see 3 of these examples have that case. Now, in case 4 here, we could have no D, no RI, and no S. And that's the very simple case of just having the RB that you looked at in the last activity. So in this example here, where we just have an RB and an RI, that's the same thing as both 1 and 2 over here. There's no S and there's no D. Here's an example where we have no S, but the other 2 pieces. Here's an example where we have no D, but the other 3 pieces. And here is an example where we don't have the RB and we're just using S and RI. And so that means no D and no RB in this example here. And that's why I have the 2, 3 right there. Okay, so now let's look at these with a real example so you get an idea of how this is done on the machine. And then after that, I'll give you why we have all of these. All right, so here's our example. Let's say that we have an address already in RDX. We're somewhere in the middle of our code, and it contains this address here, F000. And then RCX also has an address, and it is hexadecimal 1000. Now here's our explanation of how we do this, right? So that you have this here to remember how this gets done. And then here's our notes about when we don't have an S or a D, what we do. And so, or an RB, S, D, or RB, what we do if we don't have those. Okay, so let's look at this first example really carefully. So what do we have here? We have an RB in RDX, okay? Because that's there in this sample general case. We also have a D, but we don't have an RI or an S. And so in that case, we're going to simply add the displacement to RB. So we're going to take what's in RDX here. That's F000, right? That's an RDX up here. We're going to take that, and we're going to add the 8. And so the result of that is a new address. So we're taking RB and D in this equation here. And that results in F008. So when this is in assembly code, it'll turn into this value here. So we compute it using this, and we get this value here. This is similar to things that I may ask you to do on the next quiz. Okay, so now let's look at these other examples to see how this is working. So in the next case, what do we have? We have an RB, and we have an RI, but we don't have an S. And so we're going to have S be implied as 1 here. We don't have a displacement either. So we're going to take what's in R dx, and we're simply going to add what's in R in the register Ri, which happens to be what's in Rcx. So we're going to take this 0x1 and add it to the 0xf000. And this luckily can be added pretty easily in our heads with hex 0xf100. Now the next case, we're adding the S in. So there is an S. So now we will take this 4 times what's in RCX and then add R dx. So it's very similar to the one above, except now we're going to take 4 times that. And luckily this one too is pretty easy for us to do in our heads and ends up being this address. And that's the one that'll be accessed in memory, given this way of expressing the memory address. All right, so let's look at the last one. Finally, we have a displacement here, but we don't have the first register. There's just a comma there, and that's how we show that this first register RB is missing. And so note that. You'll see examples that have a comma, and that implies it'll be 0. So we just won't include it in this equation. We'll simply use this part of the equation to compute the memory address. So what does that mean? We're going to take what's in R dx and we're going to multiply it by 2, and then we're going to add that displacement that's out front. Now this one's a little bit trickier to do in our heads, but I will just tell you that this turns out 2 times F000 turns out to be 1E000. If you want to check that for yourself, you can do that on your own, but you could also take my word for it. So there we have it. There is some examples, and there are more examples in practice problems in the book that I've listed on the schedule. So you could go and look at those and try those as well. Now here's that same information in a second slide in the handouts, just so you have it. Now, you might be wondering, well, why in the heck do we need to do all this? Why do we have all these various addressing modes? And I'm going to give you one simple example of why the machine was designed this way. And then later on, we're going to see how this math that we can do here has been co-opted in some really crazy, interesting ways.